All right, so now we're going to talk about this idea of the generalized Pythagorean theorem. So if you recall the last time, we introduced this idea that if you look at the inner product of two vectors, and in particular you look at what happens when you parallel transport those two vectors, right? In order for that inner product to stay constant with respect to the parallel transport, you need that one of them is parallel transported. It's like with the primal connection, one of them is parallel transported to the dual connection. Okay, so of course it's like in the Pythagorean theorem as we typically understand it, right? You have two straight lines. It's like which, and they meet. It's like at a right angle. Okay, so so that's to say that it's like they're perpendicular to each other. So the natural way to if you're on a sort of Euclidean space, what happens is that you have, say, a vector v and a vector w, right? And at this point, it's like they're right angles, so v inner product of w is 0. And then it's like this line is a straight line, and this line is a straight line, right? So, so this is a straight line, and this is a straight line. Okay, so now we want to try to generalize this setting to sort of this dually flat case. Okay. So now you have 3 points. Let's call them Q, R, and S. Okay, so you want it's like that, that the tangent vectors is like to these two curves. It's like at this point Q, you want that inner product to be 0, right? So in keeping with this condition that it's like these two curves, it's like meet at a right angle. Okay, so so if this is V and W again, I want that V and W is equal to 0, right? But again, if you recall now, the next thing you have to do is then to say, well, okay, so these two vectors meet at a right angle with respect to this notion of a Riemannian inner product, okay? But then you have lines, straight lines emanating out of it, okay? So if you recall, it's like the analog of a straight line. In this setting of manifolds, one notion of it is this idea of geodesics, okay? So what you expect is that these curves are geodesics. So it's a geodesic, and this is a geodesic, okay? But if you recall, it's like there are two different notions of geodesics because there is a primal connection and a dual connection in this dually flat manifold, right? So and because of this idea that metric compatibility, it's like of parallel transport requires parallel transporting one of the vectors with the primal connection and one of the vectors with the dual connection. What's going to happen is that we're not going to use the same notion of geodesics for both of these curves. All right, so one of them is going to be a dual geodesic. So let's say this curve is the dual geodesic, and then this curve is the primal geodesic. Okay. And then that's going to be what we consider to be the generalization of the setup for the Pythagorean theorem in the Euclidean space, the generalization to this dually flat manifold. Okay, so to recap, what's going to happen is that you have a pair of vectors at a point Q whose inner product, it's like vanishes. So this gives you the orthogonality condition. And then it's like, say, along this vector V, I'm going to look at, say, a primal geodesic. And then along this vector W, I'm going to look at a dual geodesic. Okay, and somewhere along these curves, it's like I'm going to have the point R and S, and then there's another curve there. It's not a curve, it's a line. Well, actually, it doesn't really have to be a line. Yeah, but well, I'll just leave it there. Okay. So let me sort of state the generalized Pythagorean theorem. So, and this is expressed in terms of the divergence functions, right? Okay, so generalized Pythagorean theorem. So it says that, so when triangle PQR is orthogonal such that the dual geodesic connecting Q to R, sorry, so P and Q, where am I saying? So that's not S, so this is P, I'm sorry. So the dual geodesic connecting P and Q, dual geodesic connecting P and Q is orthogonal to the geodesic connecting Q and R. And this generalized Pythagorean relationship holds. Okay, which is that the divergence between P and R is equal to the divergence between P and Q and the divergence between Q and R. If you recall, the divergence between 2 points as units of square distance, all right? So this is like saying that, you know, it's like c squared is equal to a squared plus b squared, right? So this was c, this was a, and this is b, right? You have that c squared is equal to a squared plus b squared. And this is sort of like the corresponding notion here. Okay, all right. So, all right. So let's try to prove this result. And again, so I'm erasing the statement of the theorem, but it's all really encoded in this picture here and this condition, right? Okay, so let's prove this. Okay, so I'm going to write down the expression for the divergence between P and Q, right? In terms of the Bregman divergence. Okay, so this is one of the many ways of writing down the Bregman divergence. If you recall, it's like this involves the Legendre transform of the convex functions. It's like and dual coordinate systems which you have on this. Okay. So by using this kind of relationship, you can show that. So using this, you can show that the following is true. All right, I'm going to add these two things together, right? Show that PQ plus QR, minus. I'm going to try to essentially show that this thing here is 0, right? So I'm going to take this plus this minus this. If that holds, like this would be 0. Okay? All right, so anyway, so after writing this all down, it's like using this expression, what you end up getting is this inner product, this dot product. Okay, so the dual geodesic sort of connecting P and Q is theta star PQ, which depends on T, is this convex combination of these coefficients, right? And its tangent vector is theta Q star minus theta P star, right? Right, what am I trying to do here? I'm trying to show that this thing here is the tangent vector to the dual geodesic, and then as you might expect, this here is the tangent vector to the primal geodesic, right? Okay, all right, so let me just then say similarly, theta Q minus theta R is the tangent vector to the primal geodesic. Okay. So that inner product is 0 because it's like we already assumed that the inner product of the tangent vectors to the dual geodesic and the primal geodesic is 0, right? But these two vectors are orthogonal. So this term here vanishes, which proves it's like the generalized Pythagorean theorem, right? Because this plus this minus this being 0 is exactly equivalent to this state here. And again, it's like, just to recap, it's like, you apply this definition of the Bregman divergence to each of these terms. What you'll find is that a whole bunch of terms will cancel out. It's like, and what you're left with is basically this inner product between, or this dot product, it's like between two vectors, okay? And this calculation is basically identifying this vector as being the tangent vector to the dual geodesic curve, and a similar argument allows you to show that this term here is the tangent vector to the primal geodesic, okay? And then because of the fact that those two tangent vectors are orthogonal, by assumption, that term vanishes. So this vanishes, and that recovers, it's like the the expression we're trying to prove. Okay? All right. So that proves it's like the generalized Pythagorean theorem. As you might expect, there's going to be a dual version of this, all right, expressed in terms of the divergence associated with the dual of the convex functional. Okay, so let's see what happens. And then the proof is going to be very, very analogous to this one, so I'm not going to repeat it. But let me just set up the problem for you. So the theorem is as follows. This is the dual Pythagorean theorem. Okay, so when triangle QR is orthogonal, okay, such that the geodesic connecting P and Q is orthogonal to the dual geodesic connecting Q and R. The dual of the generalized Pythagorean theorem holds. Which is that the divergence, the dual divergence from P to R is equal to the dual divergence of P to Q plus the dual divergence of Q to R. All right, so what's the difference? So the difference here is that in this picture, you again have P, Q, and R, and this is orthogonal as before, but this curve here now is the primal geodesic. This curve here is the dual geodesic. Okay, and then the rest of it holds, right? But with instead of phi, it's like your phi star. Okay, so when you have the duality, it's not just that you have these dual divergence functions, but also the geodesics now are with respect to the opposite connection, right? So this was originally primal. The curve between Q and R was originally primal. Now the curve between Q and R is the dual geodesic. The curve between P and Q was originally the dual geodesic, but here the curve between P and Q is the primal geodesic. Okay, all right, all fairly natural. It's like if you stop and think about it. Okay, and yeah, and anyhow, so that's sort of this dual Pythagorean theorem. Okay, so so what's going to happen next? And the reason why the Pythagorean theorem shows up is because if you recall, it's like a lot of what we do, it's like when we're working Euclidean space and having some notion of orthogonality is this idea of orthogonal projection, okay? And a big part of orthogonal projection is having the Pythagorean theorem, it's like come into play. So where we're heading towards, if you will, is with this notion of the generalized Pythagorean theorem for dually flat manifolds, we can then also talk about this notion of orthogonal projection. It's like in the context of dually flat manifolds. And as you might expect, it's like when you do orthogonal projection, there is going to be the question of whether, well, what do you mean by that? Because again, there are these notions of primal and dual geodesics, right? So, it's like, so if you have a plane, it's like, and you want to project this onto it's like a point. Well, sorry, if you have a plane and you have a vector and you want to project this onto, say that you want to project that vector onto that plane, right? This vector component is like being orthogonal to the surface you're projecting onto, It depends on the notion of geodesic. It's like which you're going to use. It's like on that. So there's going to be, again, like a primal and a dual projection as well. And which one you choose, it's like depends on your application. Okay, so let me just stop here for now.